program for you tonight, something a little bit different, but very exciting, all on the theme of space and astrophysics. Tonight is brought to you in collaboration with spaceEU. And we have a variety of topics about exploring space, astronauts, sustainable off-world cities, humans and robots, and the secrets of stars. For those of you who don't know, Astronomy on Tap has been running for a number of years. It started in 2013 in New York City, was the first Astronomy on Tap. And since then it's spread to a number of different locations across the world, at over 40 locations. And here in Leiden, we were the first European Astronomy on Tap, and we've been going for over 3 years now. We meet once a month, locally in Leiden in a place called the Burgt, but right now we're back to doing things online. So we're very happy to bring this out to many people across the world this month. Check us out on social media. You probably have already seen us. That's probably how you found us. But we're on Facebook, we're on Twitter, we're on Instagram, and you can always email us and subscribe to our mailing list for more information. Just a note, give us a shout on the YouTube channel, on the chat stream tonight. Let us know where you're watching from. And tonight we really hope to get a little bit more discussion going with our speakers. We've got an excellent lineup of speakers with very diverse, interesting backgrounds. So if you have any questions about their talks, please ask in the YouTube chat. Do add your questions in. During the talks, we'll have some time after each talk for some questions, and then we'll maybe also have some time at the end for general questions to all the speakers. So pop your questions in the chat box or the comments box on the side, and then we'll have a moderator ask the questions. First up, we have a little bit of astronomy news before we get to the program for tonight. There's actually been 2 really exciting things in the last week and even today, kind of all in the theme of space exploration, so it kind of fits in quite nicely. The first thing is that this was last week sometime, the OSIRIS-REx project had a tag event with an asteroid called Bethany. And the tag was a touch and go. So basically for a few seconds, hit the asteroid, grabbed some samples, and is going to bring it back to the Earth. Hopefully, apparently it collected so many samples in its box that the box can't close all the way and is losing some of the samples. But it's really amazing and can tell us a lot about what these asteroids are made of, how they were formed and so on. The other really exciting thing, and this is hot off the press, NASA released this today, some studies using the Sophia telescope, which is an infrared telescope that's situated on a Boeing 747, I think it is, that flies around above quite a lot of the atmosphere to be able to see in the infrared. And they've been looking at the moon. And the really cool thing is that they've found evidence of water ices, within areas of the moon that are in direct sunlight, which is really new. They've found it before in shadowed areas where it's obviously cold, but this water can, well, this water, H2O, can actually survive probably within the lunar regolith, within sunny parts too. So this is really, really new, really exciting. So back to tonight, we have 4 exciting talks. The first 2 will be Bethany and Guillem Anglada talking about astronauts, the next generation of astronauts, and then also about sustainable cities off-world. Then we have our quiz, and the quiz you can participate in. The questions will be asked, and we will give you a link to a Google form to fill in the answers. We'll have a short break as well. Then we'll have our second 2 talks. Shahrzad Timman on human and robot interactions for space exploration, and Zsolt Keszthelyi, sorry Zsolt if I pronounce your surname incorrectly, about revealing the secrets of stars. Then we'll finish up with some more discussion if there are open questions from the chat. We'll announce the quiz answers, all importantly, give the winners and wrap things up from there. So without further ado, I'm going to pass over to Bethany for the first talk. But before I do that, let me tell you a bit about Bethany. She's had quite a multifaceted career in a number of roles at multiple different organizations, mostly focusing on public outreach and public engagement and communications. She's worked on projects like communications for the Hubble Space Telescope at the European Space Agency. She's been the communications coordinator for the International Day of Light. She also works for Space Scoop, which is actually really cool. Have a look at that. It's news stories written for children, exciting, relevant astronomy news. She really focuses on making space and astronomy more accessible for the general public. And the really cool thing is she's the first science and astronaut candidate from Atlantic Canada and hopes to make her first suborbital flight within the decade. And a fun fact about her is that she's spent a total of 10 minutes, may not sound too long, but it's pretty long in these things, in microgravity through various activities in parabolic and acrobatic flights. So over to you, Bethany, for your talk about the next generation of astronauts.
Excellent. Thank you much, Wendy, for having me. I really appreciate it. I'll try sharing the screen now. So today I'm excited. Well, first of all, thank you for having me. It's a great lineup of speakers that we have today, so it's exciting just to be part of it. And I want to talk a little bit about the concept of astronauts, because I think we're at an interesting time, because the connotation and denotation of the word astronaut is evolving. We're at a really special time where there's a bit of a shift in terms of what opportunities are available. So I'll speak a little bit about my own training, but also maybe what that speaks to in terms of the future, but also looking back as to what the history has been for selection thus far. I think just looking at this image, there's a few inferences that we can make in terms of some early astronaut classes. Firstly, being that they are all men and almost entirely all white men. So for the first classes of astronauts, this was typical. They almost all had military background, jet flight experience, and engineering training in some capacity. But I think what's more important is how this has evolved. So if we look now at classes from North America and in Europe, it is becoming more diverse. I think there's work to go, but there is an improvement in that regard. But the means by which these individuals are selected is quite the same generally around the world, in that it's an open call to which thousands upon thousands of people apply. And that list is then filtered down for those who meet the qualifications. And once they get to a low enough number, usually there are many tests. This includes medical, physical, mental, personality. I mean, they really want to get to know these people and everything about them, because everything that they're going to do is likely for the first time. And you also want to make sure you have healthy individuals that can focus on their duties while they're up there. So with this being said, this is very competitive. And all of these individuals are very, very highly regarded. For those where they come from, they're considered regional, provincial, national heroes, because they are one of very few who gets the opportunity to do so and to go to space and space flight experience. But with this being said, I think this idea of astronauts is evolving. And that is largely because of the private industry that is now introducing new opportunities for everyday people that might not otherwise be able to go. And to date, the means by which one would go to space is, as I discussed, is through the government agencies. But there's also been those who have been fortunate to be very wealthy and can pay for their seat to go. However, with the evolution of new vehicles, both suborbital and orbital in nature, there's new opportunities for people to fly. And this is how I've been able to start with the training experience in the hopes of having a suborbital flight within the next few years, is by means of commercial and private space flight. So with this being said, I think it's an interesting time that we're in terms of a change and a shift, because it will no longer be as competitive. And I'm hoping as many people as possible will get to be able to go. And with time, I think the factor of cost will diminish. So about 2 years ago, I began my training as part of a scientist astronaut organization that focuses on citizen scientists, primarily studying the upper mesospheric layer and climate change research. And it's through that organization that I've been able to develop partnerships and relationships and secure funding for a suborbital flight to conduct research on one of these flights when the time comes. But with this being said, as there's more vehicles being made, they're going to fly more often. They're not flying or going for as long. So I think what's exciting about that is this means more people can go. And those of us that are currently in this training program, we're serving a little bit like guinea pigs to test out these vehicles and how they work, and also to do some research in weightlessness. So we're not going up for months at a time, but we're going up long enough that there is still meaningful research opportunities. So that's primarily what our purpose serves as. And when I applied for this program, I was applying as a communicator. So my primary job is to be a communicator to explain to my community and my network not only what the training experience is like, but hopefully what the actual spaceflight experience will be like, and to bring back this science and this experience to hopefully encourage others to go as well. As mentioned, much of this so far has been a lot of flight training because this is how we are able to get some brief periods of weightlessness. This has probably been the biggest adjustment for me. I mean, a lot of it is just learning as much as you can, but there's also physical aspects of it, the high G forces and the low G forces, but also the weightlessness. It's not something that's easy to get used to. It's also been exciting to work with organizations that are testing out new technology. Most spacesuits, for example, cost in the order of millions, but there are now private companies that are developing their own. So they use candidates like us to test out these spacesuits during these flights to see how they work, to see what's comfortable, what's not. It's nice to be a guinea pig in that way because we can help them develop and improve their technology. And one thing that I really emphasize to them is they need something that's comfortable for those like me who are a bit on the short side. So if we're trying to be as inclusive as possible for everyone to go to space, we need spacesuits that can fit just about anyone too. So this aircraft that you see here is one that conducted parabolic maneuvers, during which at the top of the parabola, we were able to have somewhere between 20 to 30 seconds of weightlessness. So I've done flights where we've studied in both low gravity and microgravity during these flights. And I've had the pleasure of bringing research of my own. So this is a box of sand that I took from my home province in Newfoundland, and I was studying the behavior of the grains of sand. You can see now as we're weightless, it's almost like they're moving like a flock of birds or water around the little box. And this was more so a test of concept. So we are going to take this further, but the reason that I wanted to do this research is because sand has been seldomly studied in space. And this was a research concept that I got to conceive on my own and bring onto this flight to bring on a couple of the parabolic maneuvers to investigate. So now that we know it works and it's pretty cool, we're going to do it again. But it was pretty interesting because it didn't behave as we expected it to. And these are things that we want to know. I remember one of the big problems for the Apollo program was the dust that arose on the moon. And now these are the things we might want to consider on Mars. If we're going to dusty environments with a lot of sand, we want to know how it behaves in environments that are different than our own. So one thing that I really want to emphasize is that as we're moving ahead and trying to make space more inclusive for those of us that are going to go, it's important that we are as diverse as possible. When I was growing up there, I didn't have an example of where I came from. I'm someone that was doing what it is I wanted to do. And with that being said, I think it's important that we find people of all walks of life, all backgrounds that are able to experience the spaceflight experience, not only to bring a more inclusive in terms of the research and the experience that's being made, but also to inspire the next generation, because I think opportunities and the cost of spaceflight within the next 50 years is going to drastically decrease. So our kids and our grandkids will have much more opportunities than we even do now, but it's important that we present individuals that come from diverse experiences to really open that up. So I think this is what's exciting, is looking ahead to see what the next future might be and what other research opportunities are out there. With this type of training, I think we really don't want to diminish the work that astronauts and government agencies have done, because they've clearly gone through a lot of training. It's very competitive for their selection. So those of us that are doing this different type of training on our own time, we really don't want to diminish that. So I think the next evolution of Training for astronauts and the spaceflight experience in general will complement the government experience, but there'll also be two more, which will be tourism, those who pay for the experience of going to space. And then there's those of us who are going to conduct science in the microgravity environment as well. So that's my talk here today. I really thank you guys for listening. If there are any questions from YouTube, Wendy, if you're able to read them out, I'm not able to see them, but if there are any, otherwise I'm easy to find online if there are any questions. And I thank you guys a lot for having me.
Thank you so much, Bethany. I'm indeed looking at the YouTube chat right now. I don't yet see any questions, but I'm sure that people are typing them right now. So maybe we should ask a question of our own. I was wondering, what was your favorite thing during training?
Great question. I think putting on a spacesuit, the weightlessness was fun, but the fun got old pretty quick because it makes you want to throw up, and your whole job is to not let yourself throw up and to get used to a very uncomfortable feeling. So that was fun, but I don't think I've gotten tired of putting on a spacesuit, especially when you put the glass visor down over your head and you're fully immersed into it. It was quite a special feeling, and walking around and even conducting experiments within the suit while weightless, it's a one-of-a-kind feeling, and I don't think I'll get tired of that one.
Okay, great, thank you. And then I was also actually wondering, how did you come up with the sandbox experiments?
A great question. So all of my crewmates, they all had really cool experiments. I have one crewmate that's partnered with the Rubik's Cube, and she's doing that in weightlessness to see if she's quicker or slower. There's some really innovative ideas. So I was considering my background in my bachelor's degree of earth science. Before I went on to space science, I did earth science first. So I definitely have a love and an affinity for geology and earth sciences, and I was reading more into what research has been done to date, and I was surprised of how little research of sand had been done. There are some in terms of adding water to the sand to see how its strength changes, but there wasn't much in terms of how it behaves. So I remember once this video was posted online by a local news agency, it had been watched like 150,000 times within a couple days, just because it's weird and it's different. So it was pretty cool, and I still have that box, and I'm hoping to use it again on a future flight like that.
Cool, thank you. The questions are flooding in now from the YouTube channel, so I'll read some of those out for you. What qualification is required to enter the training program?
Yeah, so there are several that are taking place now, because this is, like I said, run a bit of a shift, right? So the one that I was in was a master's degree was a requirement, research experience, and having to come from a specific angle. So I had several doctors, a few pilots, and of the 12 of us that were selected at the same time, 2 of us were communicators. So that was my angle from which I was bringing to the program. I said, what can I, bring to this in terms of my skill, and what do I want my role to be? But in terms of the other things that they like to see, it is still quite similar to the government agencies. They want experience in different languages. Travel experience helps. They want to see what type of work you've had. They really are just trying to see what type of people want to serve in these, new technology innovations, and to help test them.
Yes, great. Then what was the issue with sand for Apollo missions you talked about?
Yeah, great question. So the big issue with the Apollo missions was, in fact, dust. When they first landed, it got all over the suits, it got in their equipment, and it wasn't necessarily something they had predicted when they were going for the first time. So this was considered on the subsequent missions, and it's being considered right now when we're going back. But dust got on everything. Think about cameras, think about the suits. These aren't things that you want to be, inundated with dust. It can really impede the research and the actual activities. So when I'm trying to think of what, going beyond that, what are we going to do in the future? I think it's important that we understand how sand behaves, because there will be sand for where we'll go, and depending on the different gravity environments, it could behave differently. So I think that's what I love about space, is that there's just so many questions left to answer, and the only way you're going to know is by doing it.
All right, then what is the highest G you have been under?
Good question. I've managed to sustain both +4 and -4 to date. That was a tough day. Then when I did them both in the same day, I don't know. I don't even remember if I kept my lunch down. I think that was a tough one. Yeah.
Can imagine. Okay, then I think I'm going to ask you a final question, and if you could then be so kind to go to the YouTube chat and maybe answer the other ones.
Of course, yes.
So someone asks, do you think regular citizens will be able to experience space within the next 20 years?
Within the next 20 years, yes. I think the price will still be a bit steep. I think the more we do it and the more people that go, the price will come down. I mean, 100 years ago, commercial, air travel was considered only for those who were very wealthy. So I think it'll happen. It's just a matter of time. And testing what works best. Is it space planes? Is it space balloons? It's a matter of trial and error of seeing what not only people enjoy, but what's most effective. So that takes time. It takes a lot of time to test these vehicles so that they're safe. And this takes a bit of time for us to consider then, all the people that want to go, because there's going to be a lot of people that want to go. So I do think it'll happen within the next couple decades. And I totally understand that it's hard to be patient, but I think it's something that everyone should be able to have the experience to do, because I think it's a one of a kind feeling, and that overview effect should be available to anyone and everyone who wants to have it.
All right, amazing. Thank you so much. And then I think we're going to move to Wendy again.
Yes. Great. Thank you very much, Bethany, for that exciting and interesting talk.
Thank you.
I certainly hope that you get to get your suborbital flight in the next 10 years sometime. So next up, we have Guillem Anglada. Apologies again for your name. Changing track slightly to talk about why we need sustainable off-world cities. So Guillem has a background in astrophysics. It's really interesting. He was the leader of the team that detected Proxima b, the nearest exoplanet to our Earth. So he has a bit of a thing, actually, apparently, for red planets. Both Proxima b and Mars, his other favorite planet, are both red. And maybe he can explain why Proxima b is red in the questions. But apart from his background in physics and space science, he has an interest in developing a space-based economy with a sight towards long-term sustainable operations and science from space. To this end, he's the founder of a sustainable off-world network, which is a network of multidisciplinary academics and professionals. So what he's going to talk about today is the sustainable city idea on Mars. So yes, over to you, Guillem.
Okay, so, well, thank you very much. Again, I cannot see the questions or the reactions, so let's see how this works. So what I'm going to talk to you about is something actually very recent, which we have been doing. As Wendy has mentioned, we have organized, I have started for these last couple of years, organizing a network of people that are interested in space exploration, of course, but they are not necessarily actual scientists working in space exploration. I think this is an important thing. It has already been said that space is becoming just a new sector of society, a new place where human activities should develop. So it should be also open to things that are not necessarily space scientists. We need engineers, we need biologists, we need people accountants, we need lawyers, things like this. So this is the goal of the network, trying to think about this use of space in a sustainable way. And then just to start the activities, the Mars Society last year issued a competition to build a city on Mars. So we said, okay, let's try to just, as a team, try to start working and see how well we do. And what I'm going to show you today is how we developed this concept of city. So it's a city that is not just a city that you go and build, it's a bit of a development plan. I'll go very quickly because I don't have time to go into a lot of details, but we have also social media and websites, so you can check other things there. So the idea, we call this city NUA, and here, this is like a tour for people that are arriving in NUA in year 2100. And now I'm going to guide you through the city where you are going to live. A little bit to introduce you how the city was built and why we think we reached the point of technological maturity that we can actually make this city possible at this point in time already. Okay, so The idea, again, is this concept of sustainability. The city does not only need to be able to sustain itself, but has also be able to sustain its own growth. It's not practical to ship all the things, all the housing, all the machines that are needed to operate the city to a new planet. It's just too expensive, as you will see. Expensive in terms of mass, not even money. So this is one of the ground principles that we took in our design. The second thing is that it has to be resilient. It's a bit like cities on Earth. You don't depend on a single source of energy to sustain your city, not even a single source of food or things like this. And also, it has to be an exciting place to live, because this is a city. It's not an outpost where you do go and do research, which might be done, but eventually, if we have these cities, the people want to go to live there. It's not, we cannot just pay people to go there for a few years and go back. It has to be a life choice. So in order for this to happen, it also has to be exciting. So it needs to be in the design. It cannot be just something that you added at the end. It needs to be incorporated. So with these design principles, one thing is very important is what we defined, what we call something called the city unit. So what's that? It's essentially one person plus all the resources, all the machines, all the services, all the housing associated to that person. That can also be done for cities on Earth, for example. But on Mars, you have seen many plans for building cities, colonies, and all sorts of things, but I think it hasn't been yet quantified how much it really takes. So what we need to take from the environment, ingest into the city, and then apply extreme sustainability so the thing is closed, so we don't consume it. But still, you need all these materials to be incorporated in the city. And at the end, actually, you will see the numbers for the city unit in a second. So once you have the city unit, for now is something abstract. What we have is not just a city, is a development model. So what we did is a bit of math. Basically, you have a differential equation that describes the growth of a population. We say that the growth rate has to be proportional to the people that already lives there, which leads us to how much housing, how much infrastructure each person should be kind of contributing per year. And you put that in a very simple, relatively simple equation, and you get something similar to exponential growth, and then you get some development. First, it has to be heavily dependent on imports from Earth, but then there's a second phase where this threshold of self-sustainable development is reached, so then you can grow exponentially just from local resources, and at the end, people is tired of development. What they want is to improve life quality, which is what would be now in the year 2100. Good. So again, as I said, one of the most important resources of a city is the citizens. So actually, we need to attract them. People want to go there. So how that would work? Essentially, we need to make up some system that would have incentives. And the idea is that people, of course, they are on Earth, so they can sell all their properties or even reach an agreement with a company that wants to start some activities on Mars. In any way, you have to pay some fee to pay for your ticket. And in exchange, what you get is transportation, you get a habitat, you get life support and food, and access to all city services of a welfare state like health, etc., air, water, and so on. And also you get something called the Mars City Share, which enables a local economy based on incentive, a bit like how it works on Earth. So instead of you pay taxes to the city, what you do is you contribute with your work to the city, and the city, when there is surplus, gives you credits. So every time there's a surplus on this city unit production, the city council distributes these credits among the people, and then these people can buy this extra infrastructure. For example, you want a larger habitat, you want a small space to start your own business, or you want to exchange this money for services, to go for a sightseeing tour for the volcanoes of Mars, or for example, to go for a restaurant. So that's a bit of the economic. So it's not only an engineering model, it's also a bit of a socioeconomical one as well. There's also cultural aspects that I don't have time to discuss. Good, so let me show what kind of city we made or we envisioned. This is a bit of a pictorial representation. You can see an awesome cliff on the left, and actually the city is inside the rock because of a number of reasons. It's better to get protection from the environment, thermal, but also radiation, dust, all sorts of things that can happen on Mars. So this is a bit of the schematic of the city. As you see, where you have the city built on the wall, so you have direct light, but you are still protected from radiation, except just from the light that's coming through the windows, but that's not that much. And then you have a region in the valley where you have larger domes for services, and then in the mesa on the top, you would have greenhouses, power, etc., etc. So this is, for example, one of these cylinders. So we build the city in cylinders. It's like tubes going into the rock, like 200 meters into the rock. But then all these tubes go on the face of the cliff. And then you have these gardens, for example. You can have parks. You can have kindergartens in these places. And just to show you how it would look like, this was done by Avivo Studio. It's an architectural design. Again, it's not only academics that participated here. For example, you can see how it might look in one of them, right? So it's a park. You could even go here and do camping. So it's not, don't think of a small space where you are claustrophobically closed with 1 million people. It's a massive actual infrastructure where you can do a lot of things. And this is just a scheme. You see all the city, how it's organized. You have all these cylinders with residential quarters, offices, facilities, parks, and all sorts of things. This is just an illustration, for example, how it might look like some of the residential quarters. Then, of course, the city needs food, power supply, and power. That's very important. So for this, for example, to incorporate one person in the city, we need, for example, to add these 90 square meters of greenhouses. We also need to collect nutrients. It's not only water, which we also need a lot, but also things that you need to grow plants, also oxygen, and also a lot of power. Each person, just to keep each person alive in Mars, you need around 40 kilowatts of continuous power. So all this power requires massive amount of infrastructure. On Earth, this comes a lot for free because you breathe directly from Earth, and Earth is doing most of the job. But here you would need solar concentrator technology. This is the solution we choose, but could be different. And a bit of nuclear also, because it provides a backup in case of solar storms. So this city would have everything that a normal city has. Some people ask me, oh, how it would look like? Actually, all the facilities would be the same. It's just that it's arranged in these kind of tunnels plus these domes. And then, of course, another thing that we added to the design is transport. The way to transport people from Earth to Mars is using a very large starship, like the thing that people like in SpaceX are developing, like Jeff Bezos or Elon Musk, these massive rockets that can transport 100 tons at a time. And with this, we actually designed a system and accounted how many of these launches would be needed in 50 years. This was our development plan. It's a lot, but don't need to go into details. Anyway, so how much it costs to incorporate a person? So to do this, basically, we make a list of everything you can imagine that people would need in this city, from the rockets to transport them, also the hospitals, the greenhouses, everything, and so on. Even the excavators, the trucks, the mining, the computers, everything. We then make a mapping on all the materials that we usually typically use on Earth, but then where they would be coming from on Mars, and then add all the collection, transformation, manufacture, and all these costs to produce what's called the city unit budget. So here you can see it. The numbers look a bit scary. It's a bit busy plot, so don't worry, but key points. For example, just to include one person in a city requires 1,300 tons of minerals to be mined from a planet. And you think, oh, Mars, this is a disaster. Well, on Earth, we are doing exactly the same. If you look at the numbers, the statistics, we looked at things, how are done on Earth, and it's more or less of the same order. Again, this means that probably we need to optimize this because this 1,300 tons is really a lot. Most of this is actually gravels that are needed for construction of infrastructure, roads, and things like this. Also, you need to collect a lot of water, and the CO2 of the atmosphere, you take it because with water and CO2, you make organic materials, which are used for domes and for food and everything. And a lot of power, which also means people have to work a lot more, but then you use artificial intelligence and things like this. Okay, so cannot go too much more into details, but I'll just leave you a video with the team. Let's see if this works, and I'll be done with this.
Hi, I do architecture and urban planning.
I do conveying.
I do future scenarios.
I do architecture and graphic design.
Life support systems.
Chemical engineering.
Space psychology.
I do architecture.
Mining and rock mechanics.
Fashion and art.
I'm an astrophysicist.
Architecture.
Astrodynamics.
In situ resource utilization and manufacture.
Architecture.
Brain-computer interfaces.
Space engineering.
Architecture.
Planetary geology and geochemistry.
I do economics with fish.
I do planets.
I do rocket science, and we are Sonnet.
are done.
Great, thank you so much. I can almost already imagine myself living there. That's really awesome. The very first question we got at the beginning of the talk was, how did you come up with the name?
Good question. Let me do something because I lost the share of the screen. And I want you to see the team. Do you see this, the team? Wow. Anyway.
Yeah.
Okay, it's fine. No. Sorry. It's a lot of people that contributed to this. This is not only me. I want to ask. I want to add. So you ask about. Can you repeat the question?
So the question was how you came up with the name.
Oh, the name. Yes. So it's actually it's a goddess from the Chinese mythology that kind of protected humans at the beginning. There's some mythology, and also made some 5 stones that are the pillars that protect the atmosphere of Earth. So it's kind of this goddess that protects and creates a city and protects humanity. Actually, we made a poll because we are a large collaboration. There's a lot of people involved. And then we just made a couple sessions of voting and choosing names. And finally, we end up with this one. Also, because these names of Chinese mythology, we always used to Greek and kind of European Western naming. And we thought that it would be a nice thing to have something like this, something that doesn't sound like the usual.
Awesome, thanks. Then who will the Martian trade these shares with? The Martian government? Are these shares distinct from normal currency that people trade in?
Yeah, so yeah, that's the idea of this economic model that we thought that, so we need this incentive. You don't want to send the people just to work for the corporation, let's say. And also, but the people has to contribute. So the idea is that when you get there, you get one of these shares, and every time anybody gets these shares. And you have it, and you cannot, there's a minimum that you must have, because it's kind of part of being the city. It's like your passport. So you are part of the city, you have a share. And the share gives you food, gives you everything. And then when there is surpluses, you get money out of it. And then this money, we call them micros, but it's like credits or euros or whatever, then you can use this to do anything. But for example, people can group and pull their shares together and maybe, for example, build a company or make a football club. So they organize and actually start an economy that it's based on a Mars value, because dollars and euros don't have any value on Mars. What it has value is what it's there. And in this case, the infrastructure that has been human built that can be used to live or to develop activities.
All right. And then more about the money. Can you tell me more why it is important to invest finite money, thought and time into detailed space, colonization and architecture on other planets instead of using that to improve the living environment back on our own planet?
That's an excellent question. First, you can choose to spend the money as whatever you want. The trick here is actually that the initial investment is not as high as you would think. So it's at the level of a cost of a large infrastructure on Earth. You have to send these rockets to start the city, but after that, the city goes by itself. And again, it's of the order of, for example, a high-speed train, the cost of a high-speed train going from Paris to Moscow, and much cheaper than the wars that are happening on over the world. And it is an infrastructure. It's like why we should have ships to travel the ocean. You have forests and you have agriculture in your own place. So why you need to travel the world? So this is to give the option of people to go there. And then also it's a bit of a service. People can go there, start new experiments. When you have the place settled and there is activity, the idea is that this creates this space economy. Is one of the elements of the space economy that allows this economy to start growing exponentially a bit at the beginning. It has to be carefully managed, otherwise you would predate the planet and you don't want to do that. But you create this economy, and it's like you don't go to Chile and build a telescope every time you want to make an experiment. You use the infrastructure that is there. So once we have infrastructure, can be Mars, can be the moon, then all the science experiments that we do in space and all these activities will be much more affordable. It will not cost anything else to our planet. So it's enabling this Martian economy, Martian or space economy. That's a bit of the goal here. And again, the cost is at the level of a large Earth infrastructure. It's not something crazy like that would take 50 years of all the world contributing to this. That's a bit of the also bottom line of these studies. There are also some of others that have done the same, and the numbers start to add up.
Okay, then gravity on Mars is 0.38 times Earth's gravity. Would it be hard to get accustomed to that?
Good question. I haven't been there, so we really don't know. I mean, there will be issues. I'm pretty sure about that. It might be better for example, older people. That might be easier to move around. For people that potentially are born there, who knows? And that would be a big if. For these reasons, for example, there are experiments in the ISS with, for example, trying to do reproduction of fish and simple or small animals. And it looks like as long as you have some gravity, things are okay. So zero gravity is bad for development of everything because you need the gravity vector to stimulate cell differentiation and a number of things. But as long as there is some gravity, and we are talking about 30–40% of Earth gravity, which is substantial, it should be all right, at least a priori. Of course, that wouldn't actually need to be tested. The only way to do it is doing experiments.
All right, and a final question. What are you going to do about the missing magnetic field on Mars?
The missing magnetic field is a problem for example, for protection. So this is one of the reasons why you need to design very hard against radiation. So the city is in the rock. You can still go on the surface. It's not as bad as it might look like. You need to spend several days on the surface to really get bad. But you cannot just live there most of the time and you have a nice apartment looking at the valley. No, you need to be protected. So it's not a big deal that Mars doesn't have a magnetic field, as long as you are always either buried or either under some protection that protects you from radiation. It's actually much worse on the moon, and on open space, it's much worse. On Mars, the combination of the atmosphere and the fact that then you can use the ground to kind of cover yourself most of the time, to sleep and to do many of the activities, is not as bad. It's not that bad.
All right. Well, thank you so much for this inspiring talk. And there's 2 more questions for you, actually. So it would be great if you could go to the chat and answer those. And then I think we have to move on to the games.
Thank you very much, both of you, and welcome everyone to the games. Tonight we've prepared 2 games for you. First of all, this is the link to the answer sheet that will also be posted on the chat in YouTube. So the first game is called Moon versus Pan. So one image, we're going to show you 2 images, and you have to guess which one is a moon of the solar system. And the other one is an old frying pan. So number 1. Remember, which one is the moon of the solar system? Number 2. Image number 3. Number 4. Five. Number 6. Number 7. Eight. number 9. Okay, I hope that wasn't too difficult for you guys. And we will now move on to our second game, which is Crazy Space Stories. We're going to tell you stories that have happened to astronauts or to space agencies, and you have to guess whether they're real or made up. So during a spacewalk outside of the ISS, an astronaut was blinded by the anti-fog treatment on the visor of the spacesuit. Is this true or false? Number 2, 2 Russian cosmonauts landed in the wrong location when returning to Earth and had to survive for 2 nights in the cold of Siberia. True or false? Three, NASA accidentally launched the wrong monkey into space during the Mercury program. Four, a Jupiter-Pluto planetary alignment in 1972 momentarily decreased the gravity felt on Earth. Five, on February 6, 1971, Apollo 14 commander Alan Shepard struck a golf ball in the lunar surface. That same ball was found along the coastline of Washington later that year. True or false? Six, in November 2019, 12 bottles of wine were launched to the ISS to study their aging process in space. Seven, NASA's twin study aims to prove Einstein's twin paradox on identical twin astronauts, one that spends a year on the ISS and another one that remains on Earth. Eight, recent ESA research found a promising recipe for making concrete that could be used to build a future moon base using only materials available on site. The key ingredient in the recipe is astronaut urine. Okay, and now on to our final question. It's the tiebreaker. Today, how many people have gone to space so far? So, as of today. Okay, that was it. Now we're going to go for a short break, and we will be back in a few minutes with our next set of talks. And you can submit your forms until right before we start with the next talk.
Great, welcome back everybody. I hope you've had a moment to stretch your legs, refill a drink maybe. Hope you found the quiz fun. Some of those pots and pans are quite dirty. We're going to move on with the program now. We've got 2 more exciting talks. The first one will be by Shahrzad Timman. She's a Dutch aerospace engineer with a passion for human spaceflight. One of her inspirations was really the movie Apollo 13. It's an excellent movie if you haven't seen it. She studied at Delft University of Technology. She's been an intern at the European Space Agency. She did her PhD on robot interaction, in specifically the time delays in doing teleoperations. And one fascinating fact about her is that she recently got to hang out, at least remotely, with her favorite robot. And her favorite robot is one of mine, C-3PO. So Shahrzad's going to talk to us today about humans and robots and how they interact for space explorations. So over to you, Shahrzad.
Yes, thank you very much. So yeah, let's talk about humans and robots and how they can together explore space, because that's what I'm really passionate about, because space exploration is coming to, there's a new time coming for space exploration, and I'm super excited about that. And what I really believe is that human-robot interaction will be key in the exploration in the coming decades. But before I go there, I want to go a bit deeper in the detail that you mentioned, Wendy, about Apollo 13, because it's always important for me to explain why I got into space exploration. So most of you, I hope, know who this is. This is the legendary NASA flight director, Gene Kranz, one of my greatest heroes. And he's single-handedly the reason why I entered, let's say, space flight, and why I dedicated my career to the exploration of space, and especially the moon. Because during Apollo 13, there was an explosion in the oxygen tank, and this basically got the crew in quite some danger. But with the leadership of Gene Kranz and the amazing mission control room, they were able to bring back the crew home safely with smiles on their faces, as you can see. And for me, this was so incredibly inspiring, how a group of people with different backgrounds can get together and basically make the impossible happen. So that's basically where it all started for me when I was a teenager. So talking about Apollo, some pretty interesting facts are as follows. So basically, during Apollo 15, it was the first time that they actually brought a rover to the surface of the moon with them. So that was not the first rover that had ever been on the moon, but it was the first time that a rover and a human being were on the moon at the same time, working together. And this was really special because basically the distances that the astronauts during Apollo 11 and 12 could cover, and 14 could cover, were quite smaller compared to what they could do during Apollo 15. Even if it was the most simplistic rover you can ever imagine, but because it needed to be light, weight was, every gram counts, so weight was really an issue. So it was a really light, really simple rover, but it was there, so it helped them carry the samples that they would take. They were able to bring back more samples and from farther places. So this is basically where human-machine interaction, if you will, it's a big term for that time frame, but let's just call it that, how that started back in the Apollo days. So nowadays we have different robots and also rovers, of course. So during my time at the space agency, which I continued after my internship actually, which was over, let's say, 5 years, I got to work a lot with numerous robots, and one of my favorites was the Interact rover. And the Interact rover, in contrary to basically the rover that I showed you, just the lunar rover that I just showed you, can be programmed to do a variety of operations. So when it comes to driving the rover from a distance, including ISS, taking samples and all, precision work, it can do it all. And it has a camera right on top there. So there's a large variety of things that can actually be done. And that's what we did. So for my PhD, as part of my PhD research, I did a large rover experiment in which we used the Interact rover, and in cooperation with the Dutch Air Force, basically, which provided us military pilot trainees. Because of that, we could actually test the human performance when it comes to human-robot interaction. Because when you have the human, let's say, you have the robot, but this interaction is something we wanted to quantify, and what I wanted to quantify for my research. So we did this with a large scale, let's say, experiment in which we had an obstacle course, if you will, that the rover could drive through and then to get from point A to B. In the meanwhile, we were measuring multiple metrics. So what we were actually doing, this is basically at another location. So this is behind that experimental site. And the operator here cannot see the experimental site, but can only see what the camera of the rover shows him. And basically we used different sensors to test performance metrics. So for example, we have eye tracking devices with which you can look through the eyes literally of the participant and know where they are looking at what time. This can tell us a lot about the focus and about the timing of basically the eye movement. But also we had an electrocardiogram with which we could test, we could follow the heart metrics. And this could tell us about stress levels, etc. So, well, you can actually see there's a big screen in front of them. They have a PlayStation, a simple controller in front of them. But the task that we were doing and at the scale that we did this with about 40 participants allowed us to get a lot of metrics and get some amazing conclusions from that, which we actually could use in planning our future operations on the moon, because we focused on multiple time delays. And these were time delays that are considering that the rover that you're controlling would be on the surface of the moon. And then the 3 different control locations would be either Earth, which is gives you the largest time delay. It could be the gateway, which is basically a future station, if you will, in the vicinity of the moon. And also the surface of the moon is the 3rd location. Another experiment that we got to conduct was at Airbus Defence and Space in Bremen, and which was a co-sponsor of my PhD. And basically what we did here, so in contrary to the previous experiment where we focused on the teleoperated driving, here we focus on the teleoperated sampling. So sampling, let's say, a lot of samples have been taken from the lunar surface by the astronauts, but what we also want to focus on is when we have, in the future, when we have rovers on the moon, which we can then teleoperate from different locations. We wanted to study that and go really into the specifics of having really a robotic arm that you're then controlling. So you see one of the participants, you see the different camera views, which gave the visual information to the participant. And again, in this, we used the same protocol. So again, the robotic arm itself was not in the direct vision of the participant, but they could see it through a screen. So using this, we actually, we could conclude a lot because we had a large group of participants and had some effective metrics that, well, actually some metrics that proved to be quite effective. So not only our researches that we have done over the years, but also aboard the ISS, there have been many occasions where the astronaut would actually interact with the robotic system. So here are some examples of the European astronauts. It could be as simple as driving the rover that would be, let's say, on Earth. For example, Andy was one of the astronauts that drove the rover. But for example, Samantha, who was controlling a 17-meter robotic arm to capture an approaching vehicle. So there's a lot been going on aboard the ISS, but what is mainly the purpose here was that it is technology development and let's say, or feasibility studies that have been performed from the ISS. So another thing that is important when it comes to the preparation of crew for future exploration. So again, I'm not talking about feasibility studies or let's say technological studies, but really the preparation of future crew for space exploration, let's say missions that are about to come. One of the main things is geology. So geology is very important when it comes to understanding the environment that you're in. So the picture that you see now is from some of the Apollo astronauts and their trainers. I think this was in Nördlinger Ries, which is in Germany. They actually studied a crater, and this is something that turned out to be very useful because all the astronauts that stepped on the moon were able to really bring back the scientific impressions, let's say the impressions that they brought back they could explain in a scientific manner, because they were fighter pilots. Only one of them was a geologist, all the rest of them weren't. So it was really great to bring everyone up to speed when it comes to geology. This is something that ESA has already been doing too for the past couple of years. And I think the first expedition that they started was in 2016, I believe. And the picture that you're seeing now is from 2017. I got to be part of this expedition. And what we did was we went with astronaut trainers from the European Astronaut Center, with Samantha Cristoforetti was there, an Italian astronaut. And there were multiple astronauts involved, Pedro Druck and other people who were there to support the expedition. And what we did, we also went to multiple locations, one of them being the Nördlinger Ries that you just saw the Apollo astronauts being on. But in this picture, you can actually see us in a lava tube in Lanzarote, where we covered a distance of 1.5 kilometers over a time span of about 3-4 hours. So it's not like walking a kilometer, but it's walking a kilometer up and down, and so it's a totally different condition. And these are some conditions that we can also expect when it comes to space exploration. And even though we did not have any robots or any robotic devices with us, what was the point of this was actually to prepare, let's say, future crew or let's say support to be able to scientifically understand the environment that they're in. And one of the things that we want to do for future is also something that they have been testing out during these Pangaea expeditions, is to eventually test both the robotic systems and the crew, let's say, together in that environment. So you see here a future, let's say, selected astronaut, but he has not flown yet, hopefully soon, Matthias Maurer. And with let's say, a simple rover that he also took with him in that same lava tube. This was the week after our expedition. And what you can actually see here is that these robots are basically prepared, and let's say it's a whole different kind of wheel structure and everything, because you have to take into account all the obstacles that they will face. They have to take into account the surface that they are driving on, and also the interaction with the operator, because there are areas on the moon, for example, where the human will not be able to go because of safety measurements, but the rover can then be sent and controlled and sent, for example, under a boulder or any other place which is not safe for the human. So this is basically the future that ESA is actually working on as we speak. And yeah, this is what I wanted to share with you today, and I'm looking forward to your questions.
Thank you so much. Again, that was really great. And we already have 2 questions for you in the chat. So the first question is, have you heard of the lunar zebra? And if so, what can you learn from, what can they learn from you, and what can you learn from them?
If I'm not mistaken, it is a project by the TU Delft researchers. Is that correct? Does it say that? Because I got to speak to one of the researchers, I think, just before the pandemic started. And I believe they also are doing, if this is the right project that I have in mind, also doing research. Yeah, okay, great. I got the confirmation. Yes, of course. I think they focus mostly on the mobility of rovers, which is great. I mean, the more, the better at this moment, because mobility is one of the challenges, because it is not as flat as you see in this picture. Robotic elements are very expensive, and we have to make sure that we don't lose a vehicle, because if we lose a vehicle, we sometimes lose a mission or part of the mission. So the more we understand about mobility and how we can actually move forward without blocking or losing a wheel, the better.
All right, thank you. Then a question, what were surprising learnings from the remote control experimentator?
Yeah, so it was interesting. What was for me, what I was hoping for is that the protocol that I set up would show the same results or similar results in both the driving experiment and the sampling experiment. And that happened. So I was really happy about that, which means that you have, comparing two large experiments, you have something to work with, and you can know what to predict when it comes to future studies. What we saw and what we really wanted to prove is we wanted to quantify the increase or decrease in performance from the human when it comes to the, let's say, the difference in time delay. So we can now, let's say, we've quantified that the, as expected, of course, that the performance of the human will go down significantly as the time delay goes up. And what we studied was 3 different time delay scenarios. So the first one being 0 delay, so no delay. The second one being 0.5, which is expected to be the ideal delay from Gateway to the moon. And a third one being 3 seconds from Earth. So we did find a significant performance decrease when it comes to the delay or the control of the robot when controlled from Earth, so from the largest time delay, as compared to the ones that have a smaller time delay. So these are some of the results that we found, and there is much more behind that. So there will be papers coming out soon, which I'm happy to share.
Cool, thanks. That makes sense indeed about the time delay. It's almost like playing a video game, but then not having the full control.
Yes. And I want to mention that the reason why we did this is, of course, we know the fact that it will go down. We know that the performance will go down if you control it from Earth, but we need to know how much it will go down. And this is what we were able to quantify. Because when you prepare a mission to the moon, and if you want to send an expensive vehicle to the surface of the moon, to another planetary body, we need to understand what we can expect from our operators that are either on the moon, on the Gateway, or on or on Earth. So that's basically why we went into the focus of especially these 3 conditions, because it covers basically all the control scenarios for these future moon missions.
All right, thank you so much. Those were all the questions from the chat. Maybe me myself can ask a final question, because actually usually when I look at the Martian rovers, they are very slow, like very, very slow. Are they slow because they're more accurate when they slow, or is there another reason?
That's interesting, because when it comes to the Martian rovers, of course, Mars is farther away from the moon, needless to say, but this also brings along a different time delay. So when you want to control a rover that is on the moon, on the surface of the moon, we have, again, as I mentioned, it's still an ideal value, but 3 seconds to 5 seconds is something we can count on. When it comes to Mars, control from Mars, we're talking about minutes, 20 minutes and up, you know, so it's not like we can actually perform a live operation. So these robots are actually designed to perform tasks autonomously. So don't get me wrong, it's not an autonomous rover, because there's a whole crew of operators and experts and, you know, sitting all over the world who have daily teleconferences together to get this thing driving centimeters by centimeters. But the idea is that it can do things, let's say, by itself, if you will, because it's programmed to do it that way. But because of this, it has to go extremely slow. Also, they're not in a rush because their basically their research objectives are not to cover the surface of Mars within a year. No, I believe that they have covered, am I saying that right? 16 kilometers in the first 6 years or something. So that's, you know, that's not a lot, but within their research scope, that, you know, that's what they wanted to do. They wanted to drive somewhere, take samples. So it's because of the time delay and the level of automation. The level of automation is really the reason for the for basically the how fast they can operate.
Perfect. Thank you so much. I think we have to move on to the next speaker. Thank you for this amazing talk on robots. There just came another question into the chat, so if you would be able to answer that on YouTube, that would be great.
Absolutely.
Yeah, thank you. Back to you, Wendy.
Great, thanks Shahrzad for that wonderful talk. Really interesting how these rovers and humans interact actually, well, robotics in general. So now we're going to change tracks quite a bit. It's still space related, but a little less about space exploration and focusing on the science. So next up we have Zsolt, and I will ask Zsolt to pronounce his surname because I don't want to do a bad job there. But I'll tell you a bit about Zsolt. Zsolt is a postdoc. He works here at the Anton Pannekoek Institute at the University of Amsterdam. He studies the structure and evolution of massive stars, which evolve quite differently to not so massive stars. He works a lot with codes that predict the evolution of stars. And he's going to talk a bit today about some of the upcoming instruments, and there's a vast array of instruments from gravitational wave measurements, seismology, magnetometry, and what this can tell us about stellar evolution. An interesting fact about Zsolt is that he went bungee jumping right before his first international conference talk. I'm not sure if you were doing that to try and get out of doing the talk or not, but the good news is that he survived both the talk and the bungee jumping. So over to you, Zsolt, to talk about massive star evolution.
All right, thank you very much for having me. It is really a pleasure. And so I will talk about stars. And the first question we can ask is that, why stars? Why are stars interesting? And the fundamental thing really about stars is that they create elements that will be recycled over time. So there is a cosmic recycling of material in the universe, and all these materials will eventually be in clouds that will lead to a next generation of stars and planets. And consequently, all the elements we really have today, other than hydrogen and helium, were once inside a star, or at least very closely related to a star. So in some sense, it's fair to say that without stars, we would not be here today, and we would not be thinking about science and space travel at all. So, of course, in terms of traveling in space, stars are pretty important for a number of reasons. One of them is that they actually cause what we call space weather, so they influence the planetary systems by their intense radiation fields and their activity. Of course, by the evolution of a star, when they become a red giant, they can actually blow up and become relatively large. That means that they can engulf close by planets, obviously not a good prospect for habitability. And thirdly, if you think about stars, they have an enormous amount of energy. And if our civilization is more advanced, we can perhaps better harvest that kind of energy. So, of course, we can ask the question, how well do we actually understand stars? And the fundamental principles were established about 100 years ago. So Eddington was the first to actually understand that stars have nuclear fusion in their cores, and consequently, they can live for millions or billions of years. before Eddington, people thought that stars could be maybe stable for 1,000 or 10,000 years. Then Cecilia Payne-Gaposchkin was the first to understand that in the Milky Way, stars consist of 98% of hydrogen and helium and only 2% of other elements. N.E. John Cannon established a stellar classification scheme that we still use today as the golden standard to classify stars. And now I will kind of generously skip over 100 years and go to some questions that I find interesting and important, and I believe that these will motivate further instrumentation and research in the field. So basically the idea for the following few minutes is that I will very briefly say a few words about how these questions can be addressed and with what kind of instrumentation. And then second, I will just very briefly also talk about why these are interesting and what we can learn from these experiments. So in terms of observing stars, of course, the first thing that comes to mind is having telescopes. And so one of the largest telescopes that have been built was the Very Large Telescope. Right now, the Extremely Large Telescope is under construction. And as you can see, astronomers sometimes have funny names for their instrument design. And so we will see whether these will actually be realized in the future or not. So in terms of ground-based observatories, some of these have already been built and working very, very well. Some of these are under construction. Some of them are in the design phase. Basically, in the next decade, we are going to shift from a 10-meter class telescope to 30-meter class telescopes. And here at the bottom, I also have a few links for space instrumentation. Basically, what they will allow us to do is to look back much farther in the universe. And what it means, of course, is when we're looking back much farther, we're looking back also in time. So by that, we can actually have the hopes to resolve stars in the very distant universe, so distant that they could actually be the first stars that formed. And so why this is significant, for example, the very first stars presumably consisted only of hydrogen and helium. So it turns out that these 2% of other elements that we now have in stars make their evolution completely different. So stars play a very significant role in the chemical evolution of the universe, creating all the elements that we need for life. Now, another really fascinating thing is that to study stars, you don't necessarily have to have a telescope and look up to the sky. You can actually have really smart instrument design that will allow you to study stars in a different way. And I believe these are presently relatively well known. These are the interferometers that use a laser beam. And these laser beams are sent out in tubes that are about 4 kilometers long. And when something really massive, cosmic happens in the universe, for example, the merger of black holes, then that will cause what they call a ripple in space-time. And ultimately, this propagates to Earth, and it will cause a delay in measuring the laser beam. So with such an instrument design, we can actually infer properties in the very distant universe. And so far, on the left, you can see here a few number of these inferred masses of black holes, basically created from the merger of 2 black holes. And this is really just the tip of the iceberg. So here you see how massive these are, the numbers representing solar masses, so 1 times the mass of the sun. And with the next generation of instruments, we can presumably sample a lot more from the lower mass spectrum of this. So right now, from the about 10 detections, in the next decade, we're going to have about 1,000 detections. So this is going to be an extremely exciting and amazing amount of data. And of course, what we can do with that is we can ask the question, how do stars actually lead to these events? And so over here, you see the standard picture of that. You have 2 stars, a binary system. And if these binary stars are close enough to each other, they will undergo what's called a mass transfer event. The more massive one will explode, create a supernova. Hopefully, the second star will not be ejected from the system. Then it will also explode and create a black hole after the supernova explosion. So if everything works out fine, then we have 2 black holes close enough that they can actually merge and create the signal that we have been detecting. Now, yet another rather different aspect is what we call astroseismology. And there are a few satellites and instruments already that are dedicated to this field of research. And one very fascinating one coming up is called the Plato mission, probably in 3-4 years from now. Well, hopefully, I should say. And you see an instrument design over here. And what these telescopes can do is that they can measure and monitor the brightness of stars. And they are very, very sensitive to any variations in the brightness. Now, from that, we can kind of understand how stars behave and how waves are propagating inside stars, just like in a lake, for a simple example. And with that, we can actually understand the layers of a star. So the prospect of astroseismology is that we can probe different regions of stars and we can kind of look inside stars and understand where the waves are coming from. Now, what you see here is a numerical model. There is the core of the star in the center, and these kind of open tubes here represent large-scale circulations. And what these circulations do is that they transport material and energy inside the star. So with astroseismology, by looking inside stars, we can actually probe these processes and their efficiencies. All of these are actually crucial to understand how stars evolve and change by time. Lastly, we know that magnetic fields are actually ubiquitous in the universe, and many stars have magnetic fields. When we think about low-mass stars, sun-like stars, they have fully convective surfaces, and they have magnetic fields at their surface. Now, it turns out that some other stars surprisingly also have magnetic fields, but a different kind of magnetic field. Nonetheless, these magnetic fields, which we cannot see directly, we can only see their impact, can be inferred. And this is quite similar if you have used polarized glasses or if you went to a 3D movie. Then basically what we want to do is we want to understand the properties of the light. And this light can basically go through an instrument design, what's called a polarimeter over here. And from that, we can infer whether the light that was emitted from the star was in the presence of a magnetic field or not. So with this special technique, we can actually probe magnetism in stars. The significance of this is, of course, that in sun-like stars, we have massive ejections of mass, we have flares, and we have a lot of activity. And so all of this is essentially thought to be related to magnetism. In terms of other kind of stars, magnetic fields will impact the mass that is lost from these stars and also their rotation. So these stars will actually spin down very fast if they have a large magnetic field. So all is to say that all these physical components will crucially impact what we know and what we think about how stars evolve over time. So what I think is that in the next decade, there is actually a wealth of data coming in, which we have to analyze and understand. And with that, we will hopefully better understand stars and ultimately our cosmic origin as well.
All right, thank you so much for the great talk. We don't yet have any questions in the chat, so I encourage everyone to start typing. So maybe I'll ask the first question. So since we're talking about space exploration, how dangerous do you think space weather of our own sun will be for our space exploration?
So it depends. So if you talk about the sun, I believe it was in the late 70s when it caused a massive power outage in the entire province of Quebec in Canada. So it can be very significant for space travel. I would say that we are still in the beginning of understanding how these activities actually work, because we don't yet fully understand the magnetic activities in stars. So once we have a better handle on that, we can probably have better predictions. In some sense, it's quite similar to predicting the weather on Earth. We have models, we can use those models and we can study them, but we need more data and we need to better verify those and able to make reliable predictions.
Awesome, thank you. And then also you talked about the very first stars. Do you think we'll ever be able to detect those very first stars?
Yes, there should be no problem. There is a lot of research going into spectroscopy, which is basically just understanding the properties of the light and the emission process and absorption process at the surface of the star where it's coming from. And so if you think about the optical wavelength specifically, and if you look at a distant galaxy, then what you see is just basically the light from stars. If you look at a galaxy in different wavelengths, then you see different kind of things. You can see gas emission and so on. But if you look at the optical band only, then it is only just a collection of starlight. Now, the problem is that we cannot resolve the individual stars. So we see them collectively. And usually in a galaxy, there are millions of stars. But with these instruments, we can actually, hopefully, study individual stars at extremely large distances.
Awesome, thank you. I think the future for your research will be very bright. I think it would be best to later, if there are still questions in the chat, if you could go to the YouTube channel and answer them there. So thank you very much.
Thank you.
That was really amazing. Close your talk of the night. And then we're going to go back to the games, the answers.
Thank you very much, Anik, and thank you, Zsolt, for your great talk. Okay, and on to the answers for the first game. So you had to choose which one of the two images we showed you was the moon of the solar system. Number one was A, is Europa, a moon of Jupiter. For number two is also image A, this time is Callisto, another one of the moons of Jupiter. Number three was image B, is the Earth moon as seen during an eclipse. Image number four is B, Ganymede, another moon of Jupiter. Number five, it was image A, it's Io, moon of Jupiter again. 6 is image B, it's Ariel, moon of Uranus. Number 7, it was the image A, this is Enceladus on Saturn. Image 8, it's B, we're looking at Titan here, another moon of Saturn. And number 9, it's image A, and this is Iapetus in Saturn again. Okay, for our game number 2, crazy space stories, are they real or made up? Number 1, during a spacewalk outside of the ISS, an astronaut was blinded by the anti-fog treatment on the visor of the spacesuit. This was true. It happened to astronaut Chris Hadfield. He was blinded by his eyes started to tear, causing near blindness. And Houston helped by opening a valve in the helmet of the so the tears could evaporate. And after this, obviously, they changed the anti-fog treatment. Number 2, 2 Russian cosmonauts landed in the wrong location when returning to Earth and had to survive for 2 nights in the cold of Siberia. This is true. The guidance system in the spacecraft broke down, so they had to land manually. They didn't want to crash in a populated area, so they chose a remote location. And the problem was that they landed 2,000 kilometers off the plant site, and the astronauts were Alexei Leonov and Pavel Belyaev. This happened in 1965. Number 3, NASA accidentally launched the wrong monkey into space during the Mercury program. This is false. NASA indeed had many monkeys and other animals that they were doing tests on, but they never would send the wrong monkey into space. Number 4, a Jupiter-Pluto planetary alignment in 1972 momentarily decreased the gravity felt on Earth. This was false. This was an April Fool's joke by astronomer Patrick Moore in 1976. He was being interviewed in BBC when he told the listeners that they could experience this phenomenon by jumping in the air at the precise moment the alignment occurred. Dozens of people called reporting that they had floated around the room. This is, of course, impossible because the gravity, the mass of Pluto is negligible compared to Jupiter, so it wouldn't make an observable impact on the gravity. Number 5, on February 6, 1971, Apollo 14 commander Alan Shepard struck a golf ball in the lunar surface. That same ball was found along the coastline of Washington later that year. This is false, and it was another April Fool's joke by NASA this time. in 2017. 6. In November 2019, 12 bottles of wine were launched to the ISS to study their age and process in space. This is true. It's called the CommuBioS mission. The idea is to study the impact of microgravity and radiation on biological processes involving yeast, bacteria, crystals, colloids, and polyphenols. The bottles are stored in the ISS for a year, and then they are compared to standard bottles of wine on Earth after they returned. Number 7, NASA's twin study aims to prove Einstein's twins paradox on identical twin astronauts. So Einstein's twin paradox is a thought experiment in which one twin goes into space at a very high speed, and then after he returns, while the other twin remains on Earth. And after the twin that went to space returns to Earth, he's much younger than the one that stayed back. This is false. So the twin study is indeed a true mission, but it aims to study the human body response to the spaceflight microenvironment from gene expression to gut bacteria and cognition. Time is indeed moving slower on the ISS compared to the Earth's surface. So a twin that spends time in the ISS will be slightly younger than the twin that remains on Earth, but this difference is infinitesimal. Number 8, recent ESA research found a promising recipe for making concrete that could be used, to build a future moon base using astronaut urine. This is true. Bringing materials from Earth to the moon would be too expensive. So ESA has been conducting intensive research to figure out a way to use materials that are already on the moon's surface. And for a tiebreaker, how many people have gone to space up to this date? And it's 566 people so far. So congratulations to everyone that got it right or close to it. And finally, we have our 2 winners. So for the non-astronomer team, the winner is Tamer team, and for the astronomer team, the winner is Micah. So if you guys, congratulations, well done. And if you want to get in contact with us, then we will send you your prizes. And now back to Wendy.
It's a pity to hear that wine that got sent up to the ISS gets returned to Earth for analysis and they can't drink it. But it's left to me tonight to say thank you again to all of our speakers. We have some lovely beer glasses, which we will try to send to you as a thank you for the very interesting and diverse range of talks tonight. The other thing to say is thank you to all of our team here at Astronomy on Tap Leiden, those of us that you've seen online, but also those of us that have worked behind the scenes to bring you these talks tonight. And of course, thank you to spaceEU for providing our speakers tonight. Do check out spaceEU. They're a great project working on inspiring a generation of young people into science and fostering a sense of global community together through space. So thank you all. We hope to see you in November for one more Astronomy on Tap, probably online again. Great, good night.